Hi everyone, welcome to our presentation today, RTK benefits for reality model data acquisition. Today we'll be looking at spatial referencing, specifically RTK and PPK data. This is real-time kinematics and post-processing kinematics, so we'll be giving you an in-depth overview into how these processes work. And finally, we'll look at context capture, how we work with RTK and PPK data. So we'll be doing a live demo using RTK data within context capture. To begin with, we want to look at accuracy and precision. Spatial accuracy is the measurement of how close a point or position comes to a geographic true value. In other words, how close a point comes to the position on the Earth that we say that it is. Precision and scale has to do with measuring. Here we measure how close a series of measurements are to one another. In other words, we take photos of, let's say, a curb line, and we measure within real-world measurement between the ends of the curb line to get the length of that curb. So precision then would relate to how close the images are to that real-world measurement. Let's go further in understanding photogrammetric accuracy in context capture. We'll begin with reality model precision. Precision within our software is equal to 2 to 3 times the resolution. So, what impacts image resolution? We first need to consider a camera model. Resolution is equal to the long side of the sensor multiplied by the distance to the subject divided by the focal length multiplied by the length of the image in pixels along the ground. If this doesn't make sense, let's look at a nadir camera model. Here we have our sensor, the long side, and here we have our focal length. When a picture is taken, it produces a view cone to the ground. The ground distance or covered is based on the distance to the camera model. The other subject or the other parts of that model affecting it are our sensor size, our focal length, and the number of pixels within the image across the ground. Because a camera, when it takes an image, has a finite number of pixels along its length and height, the further away from the target we get, the more information needs to be placed in each pixel. You may hear this sometimes referred to as ground sampling distance, but in our case, we'll refer to it as our resolution. So by changing any of these items, including the sensor size, the focal length, or the distance to the target, we will change the resolution. Additionally, cameras with higher pixel counts will have a different resolution when all things are equal than cameras with lower pixel counts. So the pixel count also affects this resolution. So now let's talk more about spatial referencing of data. So as we mentioned, spatial referencing or spatial accuracy is trying to determine where we're at on the Earth with our photographs or with the tagging of our photographs. This can be done in several ways. So the first ways would involve RTK and PPK, but also setting of ground control where we physically tie the pictures to control points that we've placed on the surface. Sometimes within RTK and PPK setups, we'll put out control points as checkpoints. So the biggest advantage with RTK and PPK is going to be the speed at which we can actually begin our capture. So when we look at the the models here, we see ground control consists of points that are put out on the surface. A minimum of 3 would be required, but typically these control points would be spaced out intermittently across the site at the spacing that the surveyor feels is proper for the capture. RTK and PPK consist of a base station, a satellite, and a drone or a rover, you may call it. So the benefits of using this rover satellite base station setup is actually can consist of speed. So accuracy, of course, but also speed. But with this type of setup, there's going to be varying levels of accuracy that we can achieve. This accuracy is primarily dictated by the base rover setup. And with the base rover setup, there are several ways that the actual base station can be set up within the RTK or PPK network. So the first is an average float or fix, and it relies on a network connection referred to as CORS, which is a continuously operating reference station. This carries with it a high level of accuracy of up to 1 centimeter. The average single, while it's a very fast method to place the base station out onto a site, it has no real positional control. So in this method, the level of accuracy uses a base GPS to average out the position, and it's actually the least accurate method available. The manual method is actually surveying a control point where the setup will be placed, where the base station will be placed. So the base station is placed on top of a measured control. It could also be put on top of a very accurate survey control that was perhaps set up for a long period of time to achieve the spatial position. This manual method carries with it centimeter accuracy. To kind of expand a little further and give you a visual input, the base provides spatial position and the rover connects to the base and satellites providing relative position. The rover in this case is an instrument on the ground. In our case, with our UAVs, the rover will actually be the drone itself. The average fix is going to have one variable, and that is the distance from the base station that the distance that we are from the base station. So the closer we are, the more accuracy we can achieve. The manual method, as I mentioned, the base station is set up on top of a surveyed point. So this point could have been created by a surveyor, taking it from perhaps a known USGS monument, using a traverse onto your job site or your launch site, and locating the position. Or it could be the use of a highly accurate survey GPS set up for a longer than usual period of time, connecting to as many satellites as possible to generate a highly accurate fixed position. The average single, the unit is placed out onto the site and uses a GPS to provide the position. Within all our systems, the rover is the drone, and the drone uses a GPS unit, whether internal or externally mounted. The GPS in and of itself typically will not give you a high level of accuracy, perhaps within 1 meter, more or less. So again, it relies on the base station and also the satellites to get more accurate positioning. So before we go any further, we want to look at kind of or know how our, in this case, our plane or drone is capturing this data. So since we're working with RTK or PPK, and let's pull our drone into focus here. So here we have a UAV, and of course the key parts of our UAV are the sensor, which in this case is a Sony A7R camera, and we have our flight controller that knows where it's going because it has some compass and IMUs and GPS units inside this. And also we have a GPS unit mounted externally. So again, we're going to get into more detail in our slides, but essentially what's happening on a normal drone without RTK or PPK, it's using solely the GPS position. So there's a satellite up in the above the clouds, and it's trying to triangulate with numerous satellites and get a lock on the position. Now without RTK, real-time kinematics, or PPK, post-processing kinematics, this position is not going to be very accurate because you have to consider the drone is in motion. You could have external factors like buildings and so forth around you, and just the fact that it's only triangulating off of GPS satellites alone to this small unit makes this relatively inaccurate. So when I say that, it's accurate enough to tell the drone to go fly above that building and circle it, but it's not going to be centimeter accurate. In fact, the level of accuracy on a typical drone that's just using the GPS unit, whether it's internal or external, is probably going to be a meter. It could even be off more than a meter, depending on the number of satellites, how the satellites are located in the sky, and so forth. So there's a number of variables, but don't count on this position being any more accurate than a meter. Now, we can still use that because this can still, depending on what we're doing, it could be just some earthworks, it could be a photograph, it could be any number of projects that you're working on that this is a good enough accuracy. But what we're going to find out is, especially with a unit like this is a Here To GPS. There's a lot of off-the-store drones, but they're all going to work similar. So if you look at the picture in the slide, you see the satellite, you see a ground station, you see a computer, and what happens is all these things triangulate together. The drone itself, if you're a surveyor, you're familiar with a rover, and the drone becomes the rover. Okay? So when your drone is flying around, it's also not just triangulating up to a satellite, but also to an accurate positioned unit on the ground. And by triangulating these three things, the satellite, the ground unit, and the rover, the position becomes very accurate. So irregardless whether it's accurate or inaccurate, when the camera triggers, the position is fed to it from the GPS. So this drone knows where it's at any given millisecond, and it can even be set up to account for the lag in the shutter trigger so that that position becomes even more accurate or real. The other factors that may or may not be logged within that image, so when the camera triggers and the GPS is captured, it then gets tagged sometimes to the image. Other times it'll get saved to a log file and then post-processed, like in the case of a PPK unit, it might have to be post-processed. So the angle that the camera's at when the camera triggers can also be captured on some units. On most store-bought units, even with RTK or PPK, this angle is not going to be extremely accurate, and thus it's going to affect the overall accuracy. But we're going to see how context capture works with it. And so we'll begin by opening up context capture. And here we have a project started where we've imported our imagery. Down at the bottom, when we import the imagery, we've already set the imagery to ellipsoid height. So we're ready to process this imagery. So the most critical part of the process, as far as we're concerned with RTK data, is number one, verifying the type of information we have. And as I said, we've already determined that the height was the ellipsoid height by comparing it to the original tags on the imagery. Now this is RTK data. Um, just a note, some PPK data, post-process data, would require you to import the positions from a text file and overwrite those positions that perhaps were not accurate tagged to the image. With RTK data, it typically will tag it in real time, so we don't have to process or post-process anything on context capture. One note for the additional data, you want to set your vertical views only if you're using nadir imagery. And you see you have several options and so forth, but today we'll look at our imagery. It's only vertical views. We can look in the 3D view, so we'll increase the camera size, and we can see by increasing the size, if we look closely at our image positions, we can actually see the top of the image. And so this line that's on our camera position, this designates the top of our image. So if we look closely, we can tell which direction our drone was moving, assuming that the camera is facing forward on the drone. Now, if you do not have rotation information or the with your imagery, then you'll just see a spot, so you won't get the view cone. So without the rotation information as part of the imagery, you will not see this. So with that, we're going to go back to our general tab. We see our statistics. Again, we set our additional data to nadir only, and we're ready to submit error triangulation. So we'll process this locally with our engine on our machine. And because we're using accurate data, RTK data, we're going to use the photo position metadata. Rigid registration is only used for inaccurate data. So a normal GPS unit on the drone would provide inaccurate data. So it's plus or minus a meter, sometimes up to 2 meters off. And so we would definitely use rigid for that type of data. In this case, we have accurate positioning. We'll toggle photo positioning metadata. Then we'll come to our settings. And now, as of update 16, we have a new alternate engine. And as I reviewed these photos, I took notice that the photos are of a landscape where there's some open areas. So it's kind of a repetitiveness within the pictures. So we'll use this alternate engine. As a note, the alternate engine typically will take a longer time. So if you have very large data sets, you may not want to work with it within update 16. However, good news is update 17 will be out shortly, and update 17, the alternate engine speed will greatly increase. So hopefully that won't deter you moving forward. Now this seems kind of counterintuitive, because we have accurate metadata. So you would think we want to just keep the position. However, this would not be the best way to proceed here, and we're going to still use compute. So when we compute the position and rotation, if we have accurate data, then we should be able to see that the positions computed will match or be very close to matching the positions input on the geotags of the images from the RTK unit. However, the rotation will always be suspect on a small drone like this. So definitely the rotation will probably be modified. So the RTK data usually does not pertain to the rotation information. So this information, the position and rotation, is actually what we consider the exterior orientation of the camera, and the bottom optical properties are the interior orientation of the camera. And so we'll just leave those as the default. So we're going to, again, use the alternate engine for a computation, and we're going to submit it. And once it's submitted, we want to be sure that our engine is open and it will begin to process. So depending on the data set, this will vary as to how long. In this case, we have 293 photos. So it should not take too long, but just to save some time, we'll cut ahead here and rejoin you as soon as it's finished. Okay, now that our arrow triangulation is finished, we can take a look at our results. So on the general screen, we'll see all 293 photos have been included in the main component, and the resolution ranges from just over 1 centimeter to just under 1.5 centimeters. So it's a good acquisition. Everything looks tight. And take a look at our results. So we see all of our tie points, or in this case, we have our splats showing, and we can increase the size of our images just to get a better look at the orientation. But over here, let's close this, and over here in our quality matrix, we can turn on, we have an option to display the distance to input positions. So we'll see our quality matrix in real time, and we have a chart over here, our legend, that shows the purple being pretty much spot on, and the red, and there's only a few red at just a little bit greater than 1 centimeter. So a very good acquisition. The majority of the photos are less than 1 centimeter in position deviation. Now let's look at what happens if we change the quality metric from distance to the input positions to the input rotations. And so now we're looking at the distance to input rotations in degrees. So the range goes anywhere from 3.6 degrees to 11.19 degrees. So we have a few photos that are up at the 11, but most of them are in the mid-range, and so we could estimate that to be somewhere around 7 degrees off and as much as 11 degrees off. So as you can see, the rotation information on your RTK will always be suspect. So this is the way the software works, and this is the way you can quickly view the results. The other way would be to go back to the General tab and look at the quality report. And this will more or less put the results in a tabular form for you. If you have checkpoints, you could always add your checkpoints into the survey tab. But here we give you the quality report and so forth. So this is a good place for you to get started. And with that, we'll take any questions that you may have. I thank you for attending this presentation.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.